LearningMeasure.tv, science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com. Episode 5, Geometry and Measurement. Hello, I'm David Archer. This is the LearningMeasure.com podcast. This episode is sponsored by TradePub and GoToMeeting.com. First of all, I'd like to apologize for not getting a podcast out sooner. A lot of things happened in April, sort of delayed me from getting this done. Not to mention one of those being taxes. So anyway, sorry about that. Also, I'm really wanting you guys who are watching this podcast to give me suggestions. We'll talk about that later. What inspired me for the topic of this episode is my youngest daughter, who came home and was having trouble with her geometry homework. Well, she was getting frustrated, and she did the typical, "What in the world would I ever use this for?" speech. I don't think I'd ever use this geometry stuff. So I thought, well, it might be interesting to try doing something with measurement and geometry. That's why I'm doing this. Now, of course, one of the importance of geometry is, at least here, is it's one of the first courses you start where you actually learn how to think rationally. That's, I think, more important than what you actually learn in geometry. But we're going to review a few things about triangles. 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 Tri means three. A triangle is something that has three angles, three sides. We know from geometry, if you have three angles, let's say alpha, beta, and theta, we know that theta plus alpha plus beta equals pi radians, or 180 degrees. Okay, that's true of every triangle. The other thing that you might want to know for triangles is something called the law of sines, which in this case is something that says the sine of theta, let's call this length here L, this length B, and this length A. Okay, sine theta over L equals sine alpha over A equals sine beta over B. Something that's true for all triangles. You can do an awful lot with that. There's also a subset of triangles. This should be reviewed to everybody who's watching this. Right triangle is a special type of triangle that has a right angle, or a 90-degree angle, or a pi over 2 angle. Then we have the famous Pythagorean theorem for the sides of a right triangle, where C is the hypotenuse, which is the side opposite the right angle. Famous a squared plus b squared equals c squared for a right triangle. What are these signs here in this equation? Well, in a right triangle, if you have an angle here, let's say alpha. By the way, if you put a right angle here, you have the same thing. For this angle here, sine, for a right triangle, sine alpha is equal to b over c. Cosine alpha is equal to a over c. And tangent alpha equals b over a, which is sine divided by cosine. That's something you learn from basic geometry. Well, what can you use this for? Well, you can use these to measure things. In particular, you can measure our universe with triangles. In fact, we're going to get to that in a minute. Before I do that, we're going to read a little something from the sponsor here, one of the sponsors. If you're looking for a better way to present or collaborate during your conference calls, your solution is simple. Web conferencing with GoToMeeting. During your call, everyone logs on to GoToMeeting.com and your computer screen shows up on their computer screens. It's like you're in the same room. GoToMeeting is perfect for sales or product demos, training, or real-time collaboration. Plus, you're not charged per minute like other providers. You can meet as often as you want for as long as you need. With GoToMeeting, you can meet with anyone, anywhere, without ever leaving your office. You'll not only save time, but money too. See for yourself. Try GoToMeeting free for 45 days. Just visit gotomeeting.com/podcast. That's gotomeeting.com/podcast. Try GoToMeeting today. Okay, yeah, in fact, more people should be doing that sort of thing because we need to cut down on our use of fossil fuels to go to meetings. It'd be nice to do them online, but that's another story. Okay, this is ostensibly a measurement-related podcast. So we'll start with, and I wanted to do a little something about geometry. Well, the natural thing to start with is the original attempt, or the definition of the meter. Okay, the initial thought about defining, you have to define some length standard if you're going to have, develop a standard that can do measurements with, unbroken chain of inner comparison. You've got to define the base unit. Well, initially they thought they wanted to make the meter the length of a pendulum that was 1 meter long at 45-degree latitude, basically at Paris. That fell out of favor. And then they came up with the idea, which is a similar size unit, is to make the meter 1/10,000,000th of the distance between the North Pole and the equator along the meridian that went through France. So, in fact, the reason we'll go through France in a way is because you can't actually measure that distance. But if you could measure between 2 points along a latitude line, evenly spaced about 45 degrees, that started at sea level and end at sea level, you could do such a thing. Turns out the only place in the world you can do that is France. So you have, you want to know what this distance is. So first of all, you want the distance at sea level. The definition they wanted was at sea level. The definition has changed since then. But so an expedition was mounted to measure the distance. So you have the world here. Well, let's make it the world is sort of flattened. It's not circular. That was something they had to discover. And here's, let's say, France. I'm not very good at drawing countries, and Spain's down here and Italy and all that. Well, anyway, what they did, which is is they wanted to find this distance at sea level through 2 points across France. Since they know the difference in latitude, they can extrapolate from the pole to the equator once they know what the shape is. They could fit an ellipse to that data, and then you would make 1/10,000,000th of that distance. Well, how did they do that? Well, they couldn't just run a ruler across the ground. That wouldn't work very well. Wouldn't be very accurate either. So what did they use? Triangulation. They used triangles. So what they did, let's zoom in on some piece of ground and we'll start at some point. And let's say you want to measure some distance, really long distance. One way you can do it, okay, you measure a bunch of triangles. And you can make as many triangles as you want. You can do them on either side. They can be any angle you want. You can do some over here, maybe get some redundancy. Well, So you got all these angles here. So you got an angle, well, you measure all these angles, alpha, beta, gamma, whatever. Let's call them, actually let's number them. So you got some angles, theta 1, theta 2, 3, etc. So I'll call this theta 0 or something. And you got all these angles. Well, if you have a triangle, that's not a very good triangle. Say you have some arbitrary triangle, not a right triangle or anything, and you measure some one baseline of the triangle, one length, very accurately with rulers, let's say. And you measure this angle, we'll call this theta 1 and call this one theta 2 for the time being. Okay, we know L. We know theta 3, because that's equal to 180 minus theta 1 minus theta 2, or in radians it's pi minus theta 1 minus theta 2. Okay. So we know this angle. So we know sine theta 3 over L is equal to, okay, let's call this side A and this side B just for fun, is equal to sine theta 2 over B, or A. Okay. We know this, we know this, we know this. We can solve for A. A equals sine theta 2 over sine theta 3 L. Okay? So this is your measurement equation for the length of this side. And then you can repeat that with the next triangle. Let's say you did this triangle first and you knew, let's say you knew this distance first. Then you can compute these two distances. Well, you have a base here, you have a base here. You can now compute these two distances. Therefore, you can compute this distance. There you can compute, and you can work your way down the triangles. And that's exactly what they did. So they measured that distance, figured out what extrapolated from the pole to the equator, and came up with an answer for what that definition of the meter would be. Unfortunately, there are other issues like continental drift, the fact that the Earth's surface is not rigid, it moves up and down, the surface has tides. There's all kinds of problems with defining it this way. What they did discover by doing this is it didn't really matter what their definition was, as long as they had a consistent length and they just picked that and everybody agreed to it, that's the important thing. And it turns out that the measurement they made back in the 1700s was off only by, I think it was 4 millimeters. No, 2 millimeters, 2 millimeters. So it was fairly accurate. We can do better today, what the distance is at a given instance, but we don't know that. Okay, so now we have that. But as a side effect of this measurement now, which by the way, we know the uncertainty too, right? Because we can figure out from our uncertainty in angles and the uncertainty in the initial length, we can compute the uncertainty in this baseline, and then you could just add it up for your whole thing. So you could compute your uncertainty in your measurement fairly straightforwardly. In fact, let's do that. So delta A equals, it's sine theta, let's do this again. Minus it's cosine theta 2 over sine theta 3 delta theta 2 L squared, delta A squared plus L, L cosine theta 3 over sine squared theta 3 sine theta 2 delta theta 3 squared plus delta L times A over L. Okay, just squared. That was just doing some quick math. Okay, so you know what the uncertainty in your length is from the triangulation, from the uncertainty in the angles and radians and the length and in whatever unit you're using. So you can use that, and now you've got the diameter of the Earth. Well, what can you use the diameter of the Earth for? They knew the diameter of the Earth pretty much, even in ancient Greek times. There were measurements made back then that were approximately correct, that gave, they knew it was a sphere. In the ancient Greeks knew that. What do you have when you have, well, let's say you know that the diameter of the Earth. Well, what if you wanted to, say, figure out how far the moon is away? You got the moon up here. And you pick some point that's easy, some crater or something. And you measure. You pick 2 points on the Earth. You know how far apart they are. You measure from these 2 different points. You measure 2 angles, theta 1, theta 2, and you know the distance L. Well, hey, this is the same problem that we did on the surface of the Earth. We can now compute what these distances are, so we know the distance to here. There is a trickiness because everything's moving. You have to have clocks at these 2 locations so you know that you take the measurement at the same time. Not too big of a deal, and now we can do it better because we don't have to do this because we have reflectors on the moon, we bounce lasers off the moon, we bounce radars off the moon, we had things in orbit around the moon. So we know pretty much within millimeters how far away the moon is today, but you know, the Greeks figured this out. Well, now you know the distance of the moon. Once you know the distance, if you're sitting here on the Earth looking at the moon in some location, you can see what angle the moon puts on the sky. Well, if you know how far away the moon is, you can figure out how big the new moon's diameter is. Again, the ancient Greeks knew how to do this. Then we forgot it as a civilization, and then we've rediscovered it. Of course, this is off a little bit, and I won't get into why, but now you have the diameter of the moon, just with basic triangles, basic geometry. One of LearningMeasure.tv's sponsors is TradePub.com. TradePub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the LearningMeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on LearningMeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support. Well, what can you do with that? Well, hey, another famous ancient, well, not so famous maybe, ancient Greek in about 300 BC came to the conclusion that, hey, if you could, from the Earth, here's the Earth, here's the moon, here's the sun. This ancient Greek in about 300 BC reasoned, if you see on the Earth, and you see, okay, you see the quarter moon, or that means exactly half the moon is lit. Well, if that's the case, it must be that the sun, the moon, and the Earth must be a right triangle. And that's correct reasoning. So all you have to do from the Earth is when the sun and the quarter moon are in the sky at the same time, measure this angle. If you already know the distance to the moon, and you know its radius and all that, you can easily compute now the distance to the sun. They actually did that in 300 BC. They were off a bit because they were off actually, it was fairly long. It wasn't too bad, but this angle they measured wrong. But you can do that today. Now we can figure out how, you can use this method to figure out how far the sun is. It's a simple geometry problem. But we don't do it that way because we have better ways of doing it now. We can look at, we have satellites and probes rotating around the sun and other planets. Through radar and communications, we can figure out exactly the distances, and we can fairly accurately measure the position of the sun. Well, what can you do with that? Well, if you know the distance to the sun, let's try measuring something bigger. And here some people think there's controversy here, but there really isn't. Here's the sun. Okay, here's the Earth in orbit. Okay, so if you look at a star up in the sky, somewhere up here, now remember we know the distance to the sun. So 6 months apart, we know the distance between the Earth and two different positions. And we measure, let's say we measure the angle to some star. Okay. Again, a giant geometry problem. We now can measure the distance to the nearest stars by just looking at the difference in the sky, the maximum distance across the sky a star moves. Now, some of you may think, well, all the stars are moving. How can we do that? Well, first of all, we'll start off with how far we can make this measurement. Pretty much the state of the art, we can maybe measure to 0.02 arc seconds. Okay. So it turns out, using geometry, okay, first of all, 1 arc second, the distance for a star that moves 1 arc second in 6 months is called a parsec. And you know, there's another unit you might know of, light years, which is, well, they're related. It's a big out there. Well, it turns out since 0.02 arc seconds is as accurate as our measurement can go, so that means anything beyond 50 parsecs will not appear to move in the sky, even if it's moving. I mean, you can make some calculations at 50 parsecs and assume the star is moving the speed of light. You know, at best, you're going to get some really small motion on the sky, even if the star was moving at the speed of light. So this is only good for measuring distances out to about 50 parsecs. So within a sphere of 50 parsecs, we can measure the distances to the nearby stars. And we can do that with a fair amount of accuracy. At least you can figure out what it is because you know the uncertainty in this measurement. You know the uncertainty in your angle measurements. You can figure out what the uncertainty in the distance is. And obviously, as you get close to 50 parsecs, your uncertainty has to get really large. You know, for reasonably close stars, you know, it's not too bad. Then you think, okay, I'm stuck. You can use this to you can only use this out to 50 parsecs. Once you get out beyond that, you have to use other methods of measuring things bigger than 50 parsecs. So I think we'll leave that alone for now. So we'll make that as the subject of our next podcast, how to measure things bigger than 50 parsecs. And then maybe I'll reverse it and go the other direction. How do you measure the really small? Okay, again, hope this was an interesting podcast for you. If you have a vendor that has some measuring solutions of any type, any product you want to advertise in this podcast, send us an email at vendors@learningmeasure.tv. And please, every single person that's watching this podcast, send me an email at suggestions@learningmeasure.tv and give me some suggestions for what topics to cover. Anything science or measurement related is fine, even mathematics related if it's maybe has some relevance. So yeah, we really want your input. I know there's about 100 of you right now watching the podcast. I want some of you at least to try to give me some idea of what direction to go in. Okay. Like I say, that's it for this week. We'll see you next week, hopefully. Hopefully it won't be as long as a wait as this time. All right. See you next time.